Okay, welcome everybody to this workshop about developing an AVB Milan endpoint, which allows you to basically build a networked audio device. I have to admit, originally I thought it could be much more hands-on, and then in the preparation I realized I think we need to set a bit the basis about networking, about protocols. It would be going a bit too far to just create a schematic or just work on the software, but what I really want to achieve today is to set the basis so you are prepared for that work. Therefore, it would be helpful for me to get to know you a little bit, just to understand a bit where your background is. Who is more on the background of electronics engineering? So you guys come more from the software side? Good, then we focus more on the electronics today, because I think it's very helpful to find the common ground. So in an embedded system, there's always dependencies between electronics and software, and you need to understand some of the basics of the microcontroller, of the schematic of the system. So it will not really be electronics engineering, but a lot about the system design. And first of all, we will set the basis about what is AVB, what is Milan, what is the technology behind, why are we doing all this. Maybe a quick introduction about myself. I've been involved in the Milan initiative since 2016, back then on behalf of D&B Audio Technique. And it was quite an exciting time, because suddenly we were starting to work directly with competitors, like here, Martin from L Acoustics is deeply involved there as well. And this was a totally new situation. Before you think, hey, big loudspeaker brand, another big loudspeaker brand. But then you talk to each other and you realize, hey, we have a common problem. We want to use an audio network, and basically we want to use a network to get audio from A to B. And there we had identified that we had a common interest. And so we met back then in 2016. There was the very first unofficial meeting in Vienna where L Acoustics, Meyer Sound and D&B met together with Avid. Bayern was there. We said, okay, we have a set of rules that we need to find to really make that interoperable, because a network is not composed of just a single speaker or from one manufacturer. It's a kind of fragmented market. You have different components, and these need to work together. So what we typically see in a network is we have microphones, we have mixing desks and loudspeakers. Just to give a simple example, of course, there could be a lot of other tools like format converters or other signal processing devices. And in between, we have an IT infrastructure with switches. And we have, of course, a user interface, typically on a PC or a laptop, which we use to control the whole thing. And just to briefly get the terminology right, when we talk about Milan, then we typically refer to the specifications that are about the endpoints, so like devices like the microphone, mixing desk, or loudspeakers, also building up on AVB technology. When we talk about the AVB switches, then we talk about AVB. AVB is like the basic technology that we use to achieve very precise synchronization, stream reservation, all aspects that I will cover in the coming hour. The reason why we're doing all that is when we talk to users, we hear a lot of complaints about the complicated switch configuration with existing solutions, actually. You really need to become an IT network expert if you want to operate a large-scale application. Of course, you can always say for a simple setup, might easily work with the existing solutions, but we really experience issues when you want to deploy at larger scale. And that's really a matter when you have 50, 100 amplifiers in a large installation, for instance. Reliability is a huge concern, and interoperability is already introduced across the manufacturers. The background of Milan, like I introduced in 2016, it was just 5 manufacturers meeting saying, hey, we want to do this together. Now there's many more brands, and also switch brands stand behind this initiative, like Netgear, Luminex, Cisco, Extreme Switches. So you find a lot of those. And of course, many audio brands who are driving the standardization of AVB and Milan. To get that a bit more into context, I mentioned already we see this AVB technology as the network technology layer. So Ethernet celebrated its 50th anniversary last year, I think. And that's really a technology that came to stay. We're using it also in this setup for the internet connection, for sending something in the office to the printer. It's around everywhere. So this infrastructure is a given and exists. But it's also technology that keeps evolving. And originally, it was not designed to be deterministic or to handle synchronous tasks. So in audio, we know we want to have everything synchronized. We want to reduce latency. Therefore, we do not necessarily want to afford sample rate conversion. It's just more efficient if everything is synchronized. And therefore, there was an initiative to develop Ethernet further, to make it deterministic, and to implement these synchronization mechanisms. So the building blocks we have there is the precision time protocol for a common time basis in the network. We have the VLAN registration protocol, which is more relevant on the switches. We have MSOP, the stream reservation protocol, which allows us to acquire bandwidth across the whole network. And then there's mechanisms for forwarding, queuing, traffic shaping, which make the whole thing, again, more reliable. And in the coming presentation, we will take a closer look at those protocols. Then on top of that, we typically talk about solution layers. Sometimes we say, there's a protocol called Dante, there's a protocol called Ravenna, there's a protocol called Milan. In fact, it's a combination of many different protocols. There's standards that get combined into a solution, something that is really user-friendly, that is ready to be used. And Milan is basically an alternative to other existing solutions like Dante, Ravenna, A67, QLearn. There's different use cases, and especially in the live segment, but also for music instruments like recording applications, we see a lot of traction for Milan. So back then, the key points we defined were that we have these IEEE standards, and somehow there was a sense of, hey, there is a trend for standardization in the industry. Everyone understood that. But the problem with standards is you get a broad range of options and formats usually. So in order to make that applicable and user-friendly, we needed to boil it down and just pick the elements that we wanted to agree on. So in case of the common stream formats, for instance, there's an IEEE standard defining that, but what the Milan specification is doing, saying we use this particular format out of those many options. That was one common problem back then. AVB was criticized a lot for being a standard, being claimed to be interoperable, but then one manufacturer could implement a 8-channel format. The other used the same encoding, but it was encoding just one channel. So it was compliant with the standard, but you couldn't talk to each other. And that's what we are overcoming here by setting rules to make sure that one Milan device can definitely connect to another Milan device. A second problem was media clocking. So we want to achieve synchronization. We wanted to build in some flexibility to get that working. And there's a dedicated specification for that, clarifying how this works. So again, to make sure that in any constellation, in any use case, you always find a way to distribute a media clock and synchronize everything. And then a huge part of the standard, and that's really a big part, is all the enumeration, connection management, and I say basic control. So we want to be able to find a network on a device on the network. Then we want to make connections, of course. We want to get audio from A to B over the network. And what I mean with basic control is the scope of Milan is to make sure that we can transfer audio over the network. The scope is not to control a level meter or to do a mixer functionality or to do EQing, things like that. So for that, the vendors often have their specific workflow, have their specific protocols. So there's also other open standards like AE70 for that. But the scope of Milan is to do the basic things like setting a device name, setting the stream format, setting the sampling rate. So everything that is needed to guarantee that you can get audio over the network, basically. Then we also figured out that there is ambiguities in the IEEE standards. So the Milan specification attempts to clarify those. And as an optional requirement, there's also a scheme to define redundancy. That's also something I will explain a bit more in detail. But the basic concept is that you can build two independent networks. A device has two ports, so you have two independent paths. But that's something that every manufacturer, it's not necessarily relevant for every use case, so therefore it's an optional feature. You don't have to implement it, but you can. And if you do it, then there's a set of rules how to do it. Is there questions so far? And please always feel free to interrupt me when questions arise. Good. Then I mentioned already the manufacturer supporting switches. AVB was criticized for a long time for, the need for special switches that support these AVB mechanisms. I think now we can say with 11 leading brands, 148 certified switches, it's really a myth that can be busted. There's plenty of options available. Of course, it's not the cheapest switch, but when you do professional audio, when you do professional networking, then you take one of these categories anyway. And in those, you typically get AVB now. Of course, there's still work to do and more to come, but you already get a broad range. The status on certified endpoints is that currently we have 69 certified endpoints from 13 leading brands. And with my background at Join, I also know there's a lot of devices in development, so a lot of new stuff to come. And our perception on trade shows is really like, maybe 3-4 years ago it was still questioned, is it really needed? But now users are like, hey, it's there, it's come to stay, it works, and there's more to come. A topic I want to mention just briefly is one of the strengths for Milan is that there is a certification scheme. So the Avenue Alliance is the organization where manufacturers come together to do the standardization work, and it's also the organization that owns the Milan trademark basically and gives the license to manufacturers to use that trademark if you pass the certification test. So there went a lot of development effort into developing this test system, which is basically, on the lower right corner, we see the device under test, which can be power controlled. There is the so-called Profi-Sharks. It's basically an Ethernet tab. These devices here, which we will also take a closer look later on in the demo session. To analyze the network traffic against the test machine. And there is a tool to do the analysis, test report generation. And with that, you can then go to a test house. They do a quick verification again. And if you're passing everything, then you get the certificate from Avenue Alliance, and you can use the Milan logo and the Milan certification trademark on your device. That's the process. So basically, this test report can be generated by the manufacturer itself. If you have this test tool, we at Join can also do that. The test house then really does just a quick validation with exactly the same test tool, so you really know what you can expect there, and then you get the certificate. This little box is the certification trademark, and the Milan logo on the upper right corner is the logo that is also part of this trademark. This is something we will drop in later. Well, actually, maybe you take a look at these links right now. This is tools I will mention in the presentation. And if you have a laptop with you, you will also have the opportunity to connect to the network, experiment a little bit. So if you want to get one of those tools, like the Milan Manager, Nibra, Hive, this is all the controller tools we will take a closer look at later. The software tools, as said, we won't go deep into that. But if you want to play around a bit, this would be the references to the toolchain and libTSN, which is an older AVB implementation that we developed further to get Milan-compliant. And also the Milan specifications, if you want to get an impression of that, you find that on avenue.org. And the Ethernet debugger is one of the tools I will also use in the demo where we'll talk a bit about how to troubleshoot a Milan network. So a first very important topic is how can we achieve the most accurate synchronization in a network? For that, we have the PTP protocol, and one of the important differences compared to other protocols is that here we really have the switches being involved. So there's other PTP profiles where you would have only like the microphone and the loudspeaker in this example, and they exchange timing information. But what they cannot do is take into account how the timing in the switch behaves. So typically the switch is not time aware. With the PTP profile we're using for Milan, the switch is taking part in that. So you have a point-to-point communication between the loudspeaker and the switch, and between the switch and the microphone. And therefore you can get much more accurate. Here just demonstrated in a simplified version. As we're developers here, we're taking a bit of a closer look, which will also help us later for troubleshooting to understand a bit how the precision time protocol works. And that's actually quite fascinating, or I think the simplicity of it is quite fascinating. What we can do with it, we can really measure how long the data is traveling on the cable. So with that measurement and with this timestamping that we're doing in hardware, you can accurately measure how long the data, the bits, need to take over the cable. So with that time measurement, I can say this is a 1 meter connection or it's a 100 meter connection. Can really measure with nanosecond precision. So the bits are traveling with the speed of light over the cable, and we can measure how long that takes. So the way how this is done is that we have two devices, and the first thing they do is how to measure how long it takes. And the math behind that is quite simple. So we send a first packet, and when it's sent out, we are taking a timestamp in hardware. So we don't have any buffering in between. We precisely know when it was sent off. We take that timestamp, send this request message. When it comes in on device B, we again take a timestamp there, T2. Then we respond to that. So basically we can take timestamp 2, pack it into that message, transfer it over to the other device. And again, when we send that out, we're taking a timestamp here. When it's received on device A, we again take a timestamp here. So we have the information available on device A now, T1, T2, T3, T4. No, not yet T3, because that was timestamped when it's sent out. So we need another follow-up message to get that data over. So we take that timestamp and put it into a follow-up message. And with that, we have all 4 timestamps available. And we can calculate how long this time is to send a message from one device to the other over the cable. And that is information that will later be used to compensate for the time synchronization of the 2 devices. There's a question?
Yeah, can they share a clock?
First of all, they do not share a clock. They have independent clocks. How should they? So you have just a timer running. You have a clock here. Typically in an Ethernet system, it's at least a 25 megahertz oscillator. So you get a time accuracy of 40 nanoseconds, or could also be higher rates, up to 125 typically. But the minimum you can expect is this 40 nanoseconds accuracy for this timestamping. And this oscillator here is totally independent of the oscillator over there. So they cannot be synchronized. This is not yet the mechanism to synchronize it. That's what I will show on the next slide. This is just the mechanism to measure how long it takes to exchange timing information, which we can then later use to adjust the clocks.
Okay, is this assuming a symmetric delay between?
Yes, that's a simplification we do here, or assumption. We say that the data transmission into this direction takes the same time as into this one. Otherwise, we couldn't do this divide by 2 thing. Yeah.
And if you've got time device CDE, is it all aggregated together, or is the network slowed down by the slowest?
It's always a point-to-point communication. So from a switch to the loudspeaker, and then the same thing is getting applied from the switch to the microphone. And if you would add another device, like let's say the laptop would be time aware, you would have the same thing going on between switch and laptop. So it's not like you multicast a time information everywhere in the network and it takes different times maybe to distribute. You do it from hop to hop.
So maybe you'll get on later to systems that are dependent on other systems for that time flow can be worked out. So could insert the laptop into that network. That will change the timing dynamic if the laptop has to do some processing before school.
Let's look at the sync mechanism. So far on the first slide, I just explained how to measure the delay. So basically, with this mechanism, running that on each link, we can figure out how long does the transfer take here, how long does it take here. This might be a 1 meter cable, this might be a 100 meter cable, this might be a 50 meter cable. So distributing the time information takes a different amount of time depending on where you are in the network. And that's something we want to compensate later on. So this was the path delay measurement. And we can also look at that later on the wire with the Profi Sharks and see how the message exactly works. This one is now about how to exchange the sync information. So let's say the device B is the clock leader here. Then device B would share its current time with device A. So it's sending a sync message where it says, now it's 5 o'clock.
So you do require a primary clock master.
You need well, that's Dante language, I guess, that you're referring to. At this point, it's not yet related to the media clock. What we're doing here is just setting a common time base across the network. We will come to media clock later. So from that perspective, it does not really matter who in the network is the clock leader. We do not have to sync to external. There could be very special use cases where you want to sync to a GPS clock or something, or maybe you have an external system where you are forced to sync to for some reason. But typically, it's just one device in the network. You try to take a switch, typically some element where you're sure it's not going away, because that would give some instability to your network. And then from there you distribute a common time across the network. It's not yet about media clocking, it's just to find a common time. Like here in the room, everyone would adjust the clock just to have a common time base. And then later on, we can reference to that to do the media clocking. I will come to that later. I think there was a hand over there.
Yeah, maybe you just clarify the
Because you had a question about the clock leader, and there is in PTP terms, when you look at the PTP protocol, when you plug all the devices together, there is an algorithm behind going on that will select the boss in the network, the time leader for the PTP time information. So in this case, it will be device B, right? And device B has to spread his clock to broadcast it everywhere. So everybody can align to the same clock, can run on the same clock later on. And this is all about just clock.
Right.
Nothing without.
So there is an algorithm called the best master clock algorithm. And that does exactly what Martin mentioned, to select who, basically also taking into account these path delays and taking into account other information like the clock accuracy and things like that. And there is priority fields that theoretically a user could also adjust. Usually it works with the default values, but you can adjust it if you have very special requirements. And based on that information, the whole network negotiates who is the clock leader. And then from there, the next thing comes into place, which is pretty straightforward now. So if device B got selected as the clock leader, it would share its current time with the rest of the network. Well, basically, it's sending this information not to the whole network, it's just sending it to the next neighbor. So like from, let's say there's one central switch, it would send it to all the connected endpoints or the other switch. And then from that switch, it would be distributed further to the next neighbors. So it's just sending its current time. This is getting timestamped. So again, same mechanism as before. We got this timestamp when the message was sent out. So we need to get that information also over to the other device. And with that information, you can then precisely calculate not only, like, it would be like, okay, I send you a letter now, it's 5 o'clock. I write 5 o'clock on the paper, put it into an envelope, bring it over to you, and then you adjust your time to 5 o'clock. But in between there was 10 seconds of the sending process. So that's what we want to compensate. That's why we're taking a timestamp in the moment I send you the message, and then I know precisely how to compensate everything. And yes, of course, this is still simplified. This is just the most important things that are, I think, interesting to know also when it comes to analysis or to troubleshooting, to understand why maybe sometimes we end up in a situation where we see that our endpoints didn't find a common grandmaster. So that's something I would like to showcase you later on. Actually, we had the situation this morning that AVB was not yet enabled in this switch. So what we saw is that the endpoints didn't find a common grandmaster. And then it's good to know that there is this path delay measurement. There is a threshold. So if this threshold is exceeded, then that is an indication that there is a switch in between that is not time aware, that is not doing GPTP. And then you can see that in a control application, and you can say, okay, now I need to go to the switch and configure it. So that's one of the most common problems, I would say, that it was just forgotten it was forgotten to enable AVB in the switch. That's the most common problem, I would say. And after that, it usually just works. I think I won't go into too much into detail here, but as mentioned, there is different PTP profiles. So when you look also at other network solutions, you come across that. There's the PTP v1 profile around, where the switches are not involved in the whole process. You just talk endpoint to endpoint. Therefore, we don't get the same accuracy as with other protocols like PTP v2 or GPTP, where the switches are involved. And the main difference for GPTP is that we are not on the IP layer. We just are operating on layer 2. There is a ether type for that, just MAC addresses, no DHCP servers or any IP configuration involved. So therefore, it's tempting to be a bit more plug and play than the other PTP profiles. But the basic mechanism is pretty much the same, and GPTP is just a derived profile from PTP v2 at the end. Questions related to PTP? Yeah?
Where can I read all about PTP?
All about PTP. If you want to read all about it, then...
Yes. Sorry, I think I should repeat the question into the microphone. I'm really sorry about this. But if I were to find the most canonical sort of entry point to read about PTP, and I want to find
so basically for PTP, there's really a lot of information around in the web. When I prepared the slides, I was just Googling for this sequence, and I noticed a lot of that is then often pictures about PTP v1 or PTP v2 or some confused information.
That's exactly what I'm asking.
I ended up creating my own. So if you want to be really sure, then go to IEEE standards. And I mean, as a user or a developer who wants to develop an audio endpoint, you do not really need to get into that. There's solutions around existing IP that you can use. If you're really curious about network technology, then you should apply at L-Acoustics or Joint, and then you can fully get into it. But if you're curious and you want to get into that, don't hesitate to read an IEEE standard. For me, when I started to work on that back in 2012, 2013, standards were like the most horrible document to read. And now I must say I'm really enjoying it after. It's not what I read before I go to bed, but it's really cool to be in these organizations, talk with other developers who work on that stuff. That's where you can learn a lot, and it's really worth getting into it. It takes a bit to get used to it, but then you
charge for the standard, yeah. You have to pay to get to the document.
the membership fee is pretty low, 100 something bucks for individuals,
You have to pay when you're a member.
and I think, Martin, maybe you know better. As an organization, it's a bit more, but as an individual or for academics, it's usually fairly low. And for PTP, you find a lot of information on the web, so you can really read a lot.
Nobody has done a sort of reprocess of the standards for the rest of us, actually. It's the standard for nothing.
What do you mean with
I mean,
reprocessing?
just someone making a tutorial, everything you always wanted to know about it.
That's what I'm trying today.
Right. Hey, go for it. Thank you.
Yeah, thank you.
Yeah, so at this layer in the protocol, how much jitter do you experience? Can you just do this once and you know it's a perfect record of the delay, or will there be like significant variance in the timing?
That's a very good question, actually. So the timestamping we can do here on these messages have accuracy of plus minus 40 nanoseconds. That comes because we have an oscillator with 25 megahertz that gives us this accuracy. Now, of course, there's some variance the more hops you have across a network. So one of the design principles, and that's also important to understand, I think, is there was a design requirement for AVB that said assuming that you have 100 Mbit links across the network, the design goal is that we achieve a 1 microsecond offset across 7 hops. So we have an endpoint. I have another slide for that later on. You have an endpoint, you have 6 switches and another endpoint. Then you want to have a time accuracy within 1 microsecond as an offset. The jitter should be much lower and still be in this nanosecond range, actually. So that's far below 1 sample period. And that's really the goal, to be sample accurate at the end. We can also have a look at that later on the oscilloscope to see how it behaves here. Cool. I think we should go a little bit ahead. Great discussion, but still have a lot of topics with me. Just a quick hint here on also the impact of this whole time synchronization thing, especially some interesting food for thought on line arrays. So when you have many endpoints that need to behave correctly, here it's demonstrated what the impact can be in terms of frequency response, which is a very interesting consideration. AES conference paper number 18 from last fall, I think. Really just a quick run through. I think most of you have heard about these things. Unicast traffic is when you send from one device, like in this example, from the mixing desk to a laptop. It's targeted to just one device. Broadcast is you send a message out and it's meant to get everywhere in the network. So this is something, especially if the data rate gets higher, we really want to avoid, because it can overload the receiving endpoints. Then in other solutions, there's often IGMP used to get that a bit more under control, so that multicast is only going where the IGMP carrier is sitting. So with that, we get a bit more control, but it still requires configuration of the switches. And what the difference now is for AVB actually is we're still doing multicast, but each stream is getting its own multicast MAC address. So there is a protocol called MAP, part of IEEE 1722. And again, very much simplified, but the mechanism is like the device, the mixer here says to the network, please give me a unique multicast MAC address for my stream. And it's getting that for every single stream. So if it's sending 8 streams, then it would get 8 unique MAC addresses for that. And that's what helps us in the switch to uniquely identify each stream and to handle the forwarding and the traffic shaping individually for each stream. That's what later gives us a lot of control and reliability. And that is actually needed because then in a second step, we have the stream reservation protocol. So again, with just very simplified words, what the mixer then does is, hey, I want to send a stream. So is there enough bandwidth for this stream? That's basically the question it raises to the network. If there is enough bandwidth available, so the switch is basically tracking that for all streams available on the network, then it says, okay, this stream is registered, but that does not yet mean that it's forwarding it. It's only forwarding it if a loudspeaker in this case registers for that stream and says, please forward this stream to me. And then only that speaker is receiving it. If there's another one coming in, then it could also register for the same stream. So it's just, it's not duplicating the amount of data here. It's just still one stream, but then being forwarded to different destinations. That's very much simplified the stream reservation protocol, just to give you the background why it is at the end more reliable and more controlled how the bandwidth is utilized here. And that leads us to one of the myths. AVB is often told to acquire 75% of the bandwidth just for AVB traffic for audio or video streams. And this is where the IT guys come in and say, oh my God, I need this bandwidth for other control traffic, or I need it for video or for lightning. Horrible. So first clarification, if I have one stream, it only takes the bandwidth that is required for the stream. So theoretically, we could reserve up to 75% for stream, which would correlate with 360 channels on a network link, which is really a lot. But if we have only 8 channels, then it's maybe just something around 15, 16 Mbit, and it would just take a small amount while the rest is still available for control. And the other consideration here, which is very interesting, I think, considering that a maximum of 75% in the default configuration would be used for AV traffic, also implies that it's guaranteed that the other 25% are available for control. And here maybe worth to remember that in the old days, 100 Mbit was totally sufficient to do control, so we still have more than what we used for control so far. And the challenging thing is really to transfer audio. But if you end up in a discussion like this, where the IT department comes in and says, hey, you're stealing my bandwidth, no, you're actually guaranteeing them that there's bandwidth available for the other things, and nothing can take away that bandwidth, at least in terms of a AV. In terms of an AVB stream. There could still be a Dante or Ravenna stream being in that range, but not from the AVB network. So that adds a lot of reliability to the whole network. And then you can also push it further and you can say, well, if you really need 90% for file transfers, printers, whatsoever in your corporate network, maybe there's just a small AV network and it's just 48 channels which require 100 Mbit, and you want to guarantee that never ever someone would get more than these 10%, then okay, why not configure the switch to set the available bandwidth to 10%, and then the rest, it implies again that the rest is available for other things. So actually a nice way to control that better. So now we're getting to another fascinating thing, which is the queuing. So what does that mean? In this example, we have a laptop, which is assumed to send some legacy traffic, and we have two audio devices like a mixer and a microphone sending two streams. So here we have this packet from the microphone coming in with a high priority. And when we talk about queues, it basically means we have two queues where traffic can be sorted. Like we get in a packet and then we can say, okay, this is high priority traffic or it's low priority traffic. Typically a switch has up to a low cost AVB switch has 8 queues, larger switches maybe even more. So this is again just simplified. We're just having high priority and low priority to demonstrate it here. And also the other simplification we make here is we're assuming just a few packets. I think in this example it's 4 packets per transmission interval. In a real-world example, you would have 8,000 packets per second being transferred. So you have a transmission interval of 125 microseconds. Here we're simplifying that just for the purpose of the demo. So we have a high priority packet coming in. It ends up in the high priority queue because it can be identified as an AVB packet. And we're putting that in the egress queue where it's sent to the loudspeaker here. So first packet comes in, gets forwarded, sent out. Now we have 2 other packets coming in at the same time, one from the mixing desk, which is a high priority packet, and one from the PC with a low priority packet, maybe a file transfer going on. So the high priority packet would go out first. Then we have, it was a larger packet, sorry, this is 2 boxes. It's a larger packet, so these 2 packets go out first, these 2 intervals. Then the low priority queue, the orange one, is still filling up because we're still busy with high priority traffic. Sending out the green one. And again, high priority, the low priority queue still filling up. And then it can be sent out because nothing else is coming in. Yet high priority traffic coming in needs to go first. Low priority queue keeps filling up. High priority queue is getting emptied. Low priority is still full. We're sending that out, again, high priority, and so on. That's strict priority forwarding. The packet in the highest queue goes out first. So now we're enhancing that for AVB. We're doing credit-based shaping, which means we're calculating a credit, or the credit is constantly going up, and whenever we send high priority traffic out, we are decreasing that. And only if this threshold is reached, then we can send out. So maybe I was not very clear before. Before was strict priority queuing. That is not what we do with AVB. Now comes the part of what we do with AVB. So how does this go? We have 2 high priority packets coming in at the same time. We're sending that out, so the credit is going down. Now the credit needs to go up before we can send a high priority packet. So we see now we have a break here. Yeah? Then we send a high priority packet again because we reached the credit threshold. We have high priority coming in. We have no credit, so we need to wait again, and we send it. So might be a bit confusing at the first time. We're delaying things now. But the effect we get, if we continue here, is that we see that the high priority packets get nicely spaced out equally across the transmission intervals. And that helps us now in the next example, where we're also adding the legacy traffic, that we can put in the legacy traffic in between. So overall, we get a much better time behavior. Where within a transmission interval, let's say this would be this regular 125 microseconds interval, we get now the guarantee that we get one packet of each stream sent out. And we have control over that because we have this credit. So if there would be more devices, we could say, okay, there's no credit, we don't forward that, it doesn't fit in. So we get this time control here. That's the nice thing about the traffic shaping. And this slopes, how far, where we set the threshold actually, that is a parameter that gets configured based on the stream reservation protocol. So all these things get very much hand in hand. And there's no configuration required. So when a switch is AVB certified and has the AVB profile enabled, then this is the mechanisms that happen under the hood. So this is nothing you need to take any action to control that.
The legacy traffic would get cluttered if you're trying to send more than 25%, right?
Right, the legacy traffic would have lower priority then. So if I would try, so here the bandwidth in this example is really saturated, right? Yeah. So if I would have more low priority traffic coming in than what fits in here, then low priority traffic would get dropped.
Yes.
That's why it has lower priority, yes. Back to the other consideration from before, you have the guarantee that you also have the guarantee that these slots are available for legacy traffic.
There's also one more point to consider. It's not only, so the spacing we do, the traffic shaping is also done to prevent burst of packets being transferred over the network. Because if you have many sources that are sending streams at the same time, they go through the same switch and they have to go out the same port of the switch to the listening device. It might be that the switch has, the queues have a certain length. It's hardware, right? So if you create long bursts of packets, you risk to lose them because the queues inside the switch are not long enough. And by doing credit-based shaping, you give the switch time basically to process the incoming packets, send them out again, and give some breathing time. Yep. And all within the constraints and the guarantee of being able to transmit whatever you have reserved. Yeah. So you don't have to burst like a crazy.
And you have this guarantee that the audio packets are coming in within this interval of 125 microseconds. Yeah. There is no further delay than that. So you don't have to have a very deep queue to collect longer and then send it over and add latency to the whole system. You know that it won't stay longer in the switch than these 125 microseconds. And then you're ready to receive the next one.
I don't understand how that doesn't impact the available bandwidth.
Well, the available bandwidth is not really impacted. Right. If you have a 1 gigabit link, you have a gigabit link. You cannot change that. But what you can change is how you set this threshold and how this slope behaves. So let's assume something is misbehaving on this network and you would get in a third stream, but it's configured to handle only 2. Well, actually you would filter it before because you would set up a filter rule that this MAC address is not even coming in. But then for what we do here is the shaping. Yeah, it's not really the filter or forwarding rule. But this is to nicely space it out. So this avoids that on the next switch, you don't have the risk that too many packets come in at the same time. You know there is these pauses, it's nicely spaced out, and therefore it's easier for the following switch to handle that.
Does AVB define the packet length? Is it a 4096 4K packet or a 64-bit packet? Or?
Yes, there is a maximum packet length, but I think it's it's defined by the regular Ethernet packet size. So that
right,
there's no jumbo frames. Jumbo frames are not allowed, but the regular Ethernet packet size is 1,600 something bytes.
Right. So let's say your high priority purple packets there. They can be a long packet, they can be a short packet, they can be whatever they want.
Yeah. That can have different length. And of course, the threshold here, the credit, needs to be configured according to the amount of data for each stream. This is not a per stream consideration. This is a packet size and stream number consideration.
So the shaping is the only way that the network guarantees bandwidth, right? The reservation.
It's actually the guarantee to avoid congestion.
Okay.
You can, on top of that, what we also do is we have filter rules. Like if a stream is not registered, then we would block it on the incoming port.
Okay. So if you can go back to the slide where you were showing without shaping.
This was without shaping.
So can you get the bandwidth, the reservation guarantees without using shaping in this form?
You could apply the filter rules to say if a stream is not registered, then I just drop it. I do not even let it into the queue. That would be a mechanism that would sit before this one.
Okay.
But once it's in the queue, then you want to make sure that you can guarantee that you forward it and that you do not congest the next switch. That's what the shaping is for.
Can you remind me what are the green packets here?
The green packets, good point. There's something. It was a second packet in the high priority queue.
Ah, okay.
And that's also interesting to note. Maybe theoretically, if you just have a differentiation by priority code points, like other protocols do, that's not a per stream thing. That's something where you say, okay, there's a class of traffic, and that gets high priority. It has a higher priority code point, but you cannot distinguish if it's coming from any of these devices where you want to have it, or if there's maybe something else sending something that you didn't plan for. That's the main difference here. So even here, the high priority queue can still overflow. You can overload it. You just send more. The control application is not telling you whether the bandwidth is available or not. You need to plan that ahead in your Excel spreadsheet or get it somehow under control. And that's the difference with AVB due to the stream reservation protocol. You get the feedback from the network. So that's what I was showing here. It's maybe even clearer now. If someone wants to register another stream here because the 10th mixing desk is coming into the setup and wants to send another 500 channels, then the switch would give the feedback on this registration process to say, no, I don't have bandwidth available. This is maybe it's just a gigabit link and not the 40 gig link, so I can't handle that. That would be one scenario, that we run out of the number of streams. The other scenario is it's still in the range of number of streams, but I don't have the capacity to forward it, because maybe down here I have just a 100 Mbit link to the speaker, because usually it has to handle just 1 or 2 streams. And if this is already saturated and I make a connection, then I would get the feedback that there is no bandwidth available. So I know before or at the point where I make the connection, I immediately get the feedback whether this will work or not. And if it works, then I have the guarantee that it will work.
Thank you.
Oh, I need to click a lot here.
I have a question.
Yeah, please.
I'm super new to this, so this might be addressed at some point or is a given. But specifically when it comes to priorities, what determines how prioritized something is? Is it like the sender, or Is there an algorithm that
I
determines
would
this
say
is
basically you as a user at the
Okay.
end, or like in a Dante setup, you would find these guidelines how to configure the switch, because there's a certain priority field used,
Okay.
and then there's this I think it's called priority code point in the UDP packet, where you can set a priority, and that allows the switch to identify what priority class it is. It cannot distinguish per stream, but you assign a stream basically to a priority class, and that is what other switches can handle.
Okay.
I think that IEEE, there is a document or a specification stating exactly how many queues you need at least to have in a switch for the implementation of AVB.
Yep.
And then it gives you the order of packet types in which queues they go.
For AVB implementation.
For AVB switch implementations, yes.
This question was a general consideration or AVB specific? Okay, because what I just explained was the legacy system.
No, I was talking about the AVB one.
Okay, so for AVB, there you have a specific MAC address, a destination MAC address per stream. So that's the first thing that allows you to check, is this a stream that is registered or not? So that's like the first filter you apply in a switch. And then the switch, due to the stream reservation protocol and the information it gets through all the connection management, it knows what the expected bandwidth for that stream is. And therefore it can allocate the sufficient bandwidth. If you would then misbehave as a sender and send more, you might get cut down. That could happen. But this is also one of the reasons to make sure that it really works as expected, why we have the certification, because these things are quite complex. And to really make it interoperable, it makes sense to check that every device is behaving as expected.
Yeah, sorry for derailing, but no, I guess I just wanted to hear, like, if you're not balanced really well, then if you have, like, let's say a period without high priority emission, just low priority, the credit goes up a lot, and you can enter a period where, you know, high priority can just completely evict low priority for a time, I guess.
Yeah, your credit cannot go below 0. So basically the mechanism is you decrease the credit when you send.
High priority. Yeah.
And then it's going up while you're not sent.
Yeah.
And the maximum credit, of course, refers to the available bandwidth.
Okay.
So it's capped at the end. Must be. Good. Then I would propose we make the last theoretical block and then should do a quick break. So now the ultimate question is, of course, what does it practically mean for the latency? And now we're also touching base on a bit on media clock recovery. So actually what we do, because we're now across the network like this, so we have a microphone, 6 switches and a speaker here. And as we have learned in the PTP block, all these devices now have a common time base. So all are looking at the same wall clock, so to say. And what we can do now is when we sample audio here on the microphone, we can take a timestamp. So later in the schematic, we will also see, like if we have an I2S bus, where we get the audio from a codec into the microcontroller, can really look at the left-right clock, take a timestamp like on the rising edge, and reference that to the PTP time. So what we get here is the current time in PTP, and we say we want to play that out on the loudspeaker at some point in the future, which is the presentation time offset. the presentation time, at the time where it will be played on the speaker. So what we do here on the talker is we take the current time, we add a presentation time offset. Default value is 2 milliseconds, but can go as low as a half or even lower. We have this 125 microsecond transmission interval, so it won't be lower than that, but in a small setup, it can really get very low. Like 250 microseconds is really realistic if you have just one switch in between. We had the presentation time offset. The packet will travel over the network depending on how much traffic there is. It might be very quick or it might take up to nearly these 2 milliseconds. And then on the loudspeaker, we buffer it until this point in time is reached, and then we play it out. So this is what basically defines the latency. The presentation time offset can also be translated as the latency you get from audio buffer on the talker to audio buffer on the loudspeaker. So here just some practical examples. So and that's fascinating because this is not just the case if you have a single channel from the microphone. There could be 360 channels, 360 microphones or some stage boxes, and really saturating these 75% of the gigabit link. And we can still guarantee that this is getting delivered within 0.4 milliseconds. So approximately, as a rule of thumb, it's a bit more than these 125 microseconds because you need to get the packet in, you need to get the packet out, plus the transmission interval. So as a rule of thumb, you can assume this 137 microseconds per hop. So for each connection, a hop is from the microphone to the switch, from the switch to the other switch to the speaker. So 3 hops, you can achieve this 0.4 milliseconds latency. And we can guarantee that for the full bandwidth being utilized.
In all of your calculations, you are taking 48 kilohertz.
That's actually independent of, for the channel count, this is referring to 48 kilohertz, and it's based on the assumption that the talker is sending 8 channels per frame, or per stream. So maybe to give you that background, what Milan defines is that a talker can choose to have 1 to up to 8 channels per stream, because for a microphone it's maybe just a single channel, while for a mixing desk it's more efficient to have 8 channels packed into one stream. And that also implies that on the receiving side, so the listeners, like a loudspeaker, must be able to support all these variants. So the talker can choose what format it is sending, but all the listeners must be able to support 1 to 8 channel formats. And this example is based on the 8 channel per stream at 48 kilohertz with AAF encoding with a bit depth of 32 bits. Good. So just to have another practical example. So I think most of the cases, if we are looking at a Pro AV live standard setup, it's often not much more than that. There's maybe a switch at the front of house, there's another switch at the stage, maybe a third one, but not far from that. If you have something like 9 hops, it's certainly already a larger installation. But still, we could maintain a latency of 1.2 milliseconds across such a large network, also assuming gigabit. Actually, the calculation is quite complex. You can look it up in an IEEE standard. It also depends on what the maximum reservable bandwidth is. So theoretically, you could even tune it further. So if you go down with a reservable bandwidth, the latency improves. So you can really optimize a lot. It's quite fascinating. But typically, you would go with the default settings. And yeah, I'm just want to give you here some examples so you have a bit of feeling for what's possible. Also summarized here, you also see it depends on the link speed, and that's important to me to have that clarified, because there's still this rumor that AVB can only do up to 7 hops. So background on that is the design goal was to support this 1 microsecond offset and all these other criteria here, assuming that you have 100 Mbit up to 7 hops. But if you go gigabit, like in this example, you can get the same results that were defined for 100 Mbit for gigabit. So you can stay within these 2 milliseconds latency with up to approximately 14 hops. So you can go much bigger as you get more bandwidth. So that's really scaling well. But what we see mostly in endpoint implementations is either it's 100 Mbit, which can still be a good choice because you save some power, it's maybe a little bit cheaper in terms of hardware cost and processing resources, and many just use gigabit. And then this is the figures you get. Good. I think we can take a short break here. I think, yeah, I would later do a second break. I have like 2 more blocks. So the next one would now go into the microcontroller we are using in our example and talk a bit more about the schematic, the system design considerations, how this clock recovery gets implemented in hardware and software. And then the third block would be really hands-on, looking more at measurements, some troubleshooting. There we are a bit flexible depending on how much time we will have for that. Okay? Do you need 10 minutes or should we just do a short 5-minute break? We definitely have enough content, really up to you. So I really appreciate the questions and the discussions, and I really would like to keep that up. Just to adjust the schedule a little bit, are you more curious to focus on the schematic and these design aspects, or is it more the troubleshooting and getting some hands-on the existing tools and the setup here? Is there a preference for hands-on? Schematic and design considerations? So more, okay, it's 50-50. I will try to make both. So I'll just walk you through the design aspects, and then after that we will make another short break. So we have 1.5 hours now, right? Good. So we will do a quick introduction now to the XMOS microcontrollers. I have also Ross with me, so if you have really specific questions about XMOS, he's the expert for that. And yeah, just some basics on that. The interesting thing about XMOS microcontrollers and why we choose that as the first platform we are supporting is it has an architecture with many logical cores. So basically the thinking is like to divide it into 2 tiles here, and each tile has up to 8 cores that you can use. So each core can execute its own thread and has its own register set for that. And then you're very flexible in programming IOs for each tile. So you can do a lot of functionality in software. Like you don't have a dedicated I2S hardware on the chip. You just do that in software because you have enough cores and you can have one core just doing this I2S driver while others are doing other signal processing or network stuff. And also for the RGMII interface, what we need to get the network connection, that's also done in software mostly. Maybe also worth to mention, XMOS is known quite well for doing USB audio stuff. So there's also a lot of possibilities to leverage that for network applications or the combination of both. And what we can also do here is we get very precise deterministic behavior on IOs. So that's what we later want to use also for the clock recovery, that we know when there's the rising edge of a left-right clock or the frame sync of a TDM, then we want to timestamp that because we will use that to regulate our media clock recovery. And the way we use that, maybe worth to be mentioned also, there's this XConnect which is basically a communication system between the threads. So that allows you to have very fast communication between the cores. Anything else I should mention here?
I think it's a single memory for each tile.
Yeah, you can kind of think
Or use the microphone maybe?
There's a single memory for each tile, and you can kind of think about each logical core or thread as a hardware thread as a sort of its own dedicated microprocessor. So you've got 8 on each tile essentially.
But you don't have the audio circuitry like the ADC and stuff are not in there.
No.
No.
So you would typically use one core for a I2S or a TDM driver, for instance, and then interface with your favorite codec.
Is there some notion of the number of channels that this thing can process? No. And if you organize your incoming I2S, you could run that kind of.
Yeah, actually the limitation is practically more on the number of GPIOs in our application. So typically when you go higher channel count, of course you go TDM and not I2S anymore.
Yeah.
But a benchmark, what I can give you, what we're doing in our implementation is we're doing up to 64 by 64 channels, 8 by 8 streams at 48 kilohertz. And we're currently investigating if we could do up to 128 channels just on a talker. Probably not being possible for both directions, but for one direction, it might be possible to do up to 128 channels on a standard microcontroller. And that's quite fascinating. I think that you can get a microcontroller, a really affordable microcontroller that scales from a price point also for application where you can consider to use it for a single channel application in a loudspeaker or a microphone, where you may be more cost driven, but it scales up to the 64 by 64 channels. And yeah, that brings us already to how we are using that. And this basically applies to the original AVB implementation, which is open source, which you can access. It's also shared in the links. But that's the old AVB stuff. And what we have done, we have developed that further to make it fully Milan compliant. So that would be joint IP then. But this applies pretty much to both, just to give you a rough idea. And what's interesting here to consider is when we talk audio, we want to achieve synchronization at the end, right? We get audio in, we get audio out, we want to have it synchronized. But what's happening in between is a lot of asynchronous tasks. So there might be the audio coming in from another stream which is processed by the listener thread on one core. And that's something that needs to be driven very constantly with a high load with 8,000 packets per second for each stream. But at the same time, there might be a PTP packet coming in, or there's a control packet coming in from the controller for the AV protocol. And these things happen asynchronously, and suddenly we need to handle a lot of asynchronous tasks, although the end goal is a synchronous audio transfer. And that's why this is very efficient for us to assign all these different tasks. Like I2S TDM is one core, GPTP is its own thread, one for the listener, one for the talker, one just for control stuff. There's a buffer manager, basically translating between TDM and talker listener, the stream reservation protocol that we discussed, one that is just handling persistency to write and read from the flash. And then most of the other tile is used for either a 100 Mbit AVB Ethernet MAC. Then you also have still some cores available, which you could use for DSP or your own proprietary remote control stuff. Or if you do gigabit, then we need a bit more cores, and then it's pretty much used. But there's also the possibility to scale it further. So this internal X-Connect system can be connected to another package, or there's one variant where you get both packages in one device, and then you have plenty of cores for other DSP tasks.
Is this X-Connect
the physical as a bus. Can you connect one or two?
Right, you can have two separate chips, two devices, and interconnect them. Even more, right?
As a bus. This one. You can arrange it in a few different volumes. Fire or star. There's a super design.
Good, and then just a quick note on the I/O mapping. So basically the logic, and you will understand in a couple of slides why this is important to understand, is you can have different port widths. So you can have a 1-bit port, which also has the capability to serialize hardware. So like when we do a I2S driver, what we do is basically we write the whole sample as a 32-bit word, and then it's getting serialized by the hardware. So in the meantime, it can do other things in software to rearrange data or something. And then it's getting serialized on a 1-bit port. You can do similar things on 4, 8, 16, 32-bit ports. So typically the easiest way to go is with 1-bit ports for like serializing things, or deserializing, of course. For doing very accurate timestamping on a left-right clock or a frame sync. There can be some tweaks made to do that also on 4 or 8-bit ports. And typically we use like 8 or 4-bit ports for simple GPIO. So like, yeah, I have an example from a client who's making these boxes where you have just some level meters. It's a 4-channel AES3 in and out device, and you have level meters for the inputs and the outputs. So you just want to have a level meter LED. So then you can easily do that on an 8-bit port, for instance, to switch LEDs on and off, which is a comparable boring task compared to handling 8,000 packets per second. We do that just once per second, maybe. Yeah, you can synchronize I/Os. So this is something that also benefits us when we do something like I2S or TDM. Like you have a master clock coming in, and then you divide it down to the frame sync or the bit clock. And that's quite helpful to do these things efficiently. What's really important to consider is actually are these parameters, like what do you need in terms of channel counts, in terms of sampling rates, stream count, vendor strings. That's basically then just some defines. There might be considerations to do a single Ethernet port or a dual Ethernet port if it comes to redundancy or more advanced features. And of course, you typically think about what codec you want to use. So maybe you have a schematic for some AD, DA conversion stuff that you just want to reuse, and then connect it to the XMOS via I2C or TDM typically. So I think these are quite common examples and parameters. And what I really recommend to do first, it doesn't have to be a very complicated specification, but take the time to write something down. Refine that during the development process, but it's really helpful because as we saw here, we're more software developers than hardware engineers, but the hardware engineer needs this input, and there is this, especially when it comes to the I/O mapping, there is things that you will change in the process. So make it very clear how many LEDs do you need, because if it's an 8-bit port and you have 8 LEDs, that might work well. But if you start the hardware design with a 4-bit port and then at a later point it's suddenly 8 LEDs you need to drive. Get these things right, discuss it early, write it down, and then you can walk much more efficient through the remaining process. Based on that, block diagrams are always helpful, of course. I have this one here mostly to explain a bit the architecture. So a standard component you find on the reference design, which can be ours, but can also be the multi-channel reference design for XMOS, where XMOS has these Explorer kits. that sit on top here on our analog board. There you get something where you can start playing with the RJ45 connector. The AR8035 is a Ethernet PHY, which is now getting end of life, but there's an alternative from Microchip. So this is something you want to consider. There's sometimes some adjustments you need to make to the driver for that, but typically it's quite standardized how this feature set works to see if the link came up, what link speed is it, things like that. That connects to the XMOS microcontroller in our example, which does most of the work, like encoding, decoding, PTP, all those protocols. And the surrounding system is often a codec, which we connect with I2S bus. We have some analog sections. On this example, we have a system connector, which you could also use to attach some other hardware. And a very critical part, and I think this is something we will discuss a bit more, is the clock recovery. So there is a PLL component, which we basically drive with a reference signal, which is a low frequency, like 1 kilohertz, where we give a reference clock. And this multiplies it up to a typically 12 point something or 24.576 megahertz, a standard master clock that is used for the ADDA conversions. And then we do some magic again in the XMOS. So we get the master clock as an input on one of these serial ports, can do the timestamping there. We're not doing the timestamping there. So we get this as a clock, we divide it down to get a left-right clock and a bit clock. So all this is happening in hardware. It's just 2 lines of code to configure that. And with that, we're driving all the audio transfers. And what we do then is we do some timestamping whenever we get a sample serialized or deserialized. And this goes then into this clock generation here. So this whole thing forms a control loop that allows us to synchronize these clocks to the clock of another device of this type, where we're exchanging all this timing information through the streams and the PTP protocol. The just basic idea clear of that, or are there questions to this clocking things? Because that's a really critical part to understand.
Yeah, I have a question about the clock recovery PLL block there. Is it an actual external physical hardware component, or that's just a logical? The clock recovery PLL block in the diagram,
yeah.
Is that a physical hardware component, or that's just a logical?
Yes, that's typically, there is one standard part that you find in many designs from Cirrus Logic, the CS2100, which is now obsolete, but there is a drop-in replacement, for instance, available from that or from Cirrus Logic itself. I think the part number is CS2500. That's one option to go. The other one, there is the CS2600, I think, which can also do this job of providing multiple clocks. So it does the same thing, generating the master clock out of a low frequency reference. But then here we're doing the dividing it down to the 48 kilohertz, or the bit clock is done on the XMOS. With the newer part, you could do that directly on the Cirrus Logic part, which saves you some GPIOs there, or you would then, well, you would still need them, but you're getting some more flexibility. You would then do a TDM slave or a I2S slave here, rather than being the master, which can be beneficial if you have a more complex system, where you maybe have multiple XMOS chips or other DSPs that you also want to synchronize.
And the idea of that that component is to get 2 clocks and 2 different clock domains, and basically be able to get a synchronized clock out of that. Like, so if you get a
synchronized clocks, maybe we need to briefly clarify what the I2S or TDM bus is. So On the I2S bus, you would have a master clock, and then
Yeah.
synchronous to that, you have the word clock, the left-right clock,
Right.
running at 48 kilohertz, and you have a bit clock,
Yeah.
which is a multiple. Again,
Right,
of
but
that.
how do you translate? The point is like you have to translate that into the PTP clock, right? So you get the simple accurate
Yeah.
timestamps.
No, we do not Well, the PTP clock itself runs on its own.
Right, but
And
it's
then
running
we
on a
have,
different clock,
of course,
right?
we have a local timer here, which is not exactly the PTP time. It's first
Right,
it's
exactly,
a local
yeah.
timer.
Yeah.
So that's the timestamp we get.
Right.
That's typically just a 100 megahertz clock driving that, and that needs to be converted into
Right.
PTP time to then get a PTP timestamp into the Ethernet packet.
Exactly.
Yes.
And is that what the clock recovery does, or that's done inside the DSP?
No, this part is actually part of the encoding and this whole mechanism behind.
Okay.
What we mean with clock recovery is actually, we will also take a look here at the setup and with the oscilloscope. So currently, let's do that maybe now. Currently, we have two devices connected.
Yeah.
So you see the two left-right clocks
Yeah.
of two boards that are connected to the network.
Okay.
PTP is running. They have a common time base, but obviously these clocks are not synchronized.
Right.
They're drifting, right?
Yeah.
So what we do then in the next step is we will connect AVB stream. I will show that later in the demo. We will have more time for that then. But what will happen when I connect the stream is that I'm getting timing information. Like on this device, I take the timestamp on the edges here.
Right.
I convert that into PTP time. I add the presentation time offset, send that over to the other device. And here I can then measure, I know, okay, now is the presentation time. I should have an edge here, but I'm getting it there. So I can measure this difference, and then I can run this control loop to adjust that.
Oh, okay.
So I can speed up the clock or slow it down
Okay.
until these get in sync.
So the
I will show later
control loop
that
is
we will
used
get
for
them in
like
sync.
drift correction and for if there's two different clocks drifting from each other. Okay.
So currently the state is not synchronized. We don't
Right.
have any connection, but PTP is already active. That's one thing.
And on the
then
sync
reference to
sync part, when you send over the network, do they have to also synchronize different streams? Are they actually now they are running at the network clock?
Well, you can only choose one stream to sync to. You have
Right.
one local clock
Yeah.
at the end, and at the end
But
you
do-
want
do-
to have
do
all
they have to do
devices
that?
being synchronized.
Like
So
is that
theoretically, you could build a setup where you have maybe two independent networks. You do two clock recoveries.
okay?
Theoretically, it's possible. I haven't seen the use case yet where anyone did that, but you could do it if you say you strictly want to separate two clock domains and receive from both, and then maybe do a
Right,
separate
right.
conversion in between.
But in this case,
Do
you
that.
have two sources right there. And in this case, if you send them, if the timestamp is synchronized with the PTP clock, then on the sync side, the receiver, they don't have to synchronize those two sources, right?
Maybe also to clarify here, you do not necessarily sync to the PTP clock. We
No?
use the PTP clock only to reference to
Oh,
the
okay.
common time base, but it does not mean that we need to be in sync with the PTP clock.
Okay.
But what we will achieve is that the media clock of device A is getting in sync with the media clock of device B. We're using PTP
Right.
to get that mechanism
Together.
to work. But the media clock oscillator is independent of the PTP Ethernet.
Right. So it might be that on the sync side, they still need to do some ASRC or something if they want to mix those two signals together.
If you want to mix those together,
Yeah.
you want to configure it in a way that you achieve the synchronization. And
Right.
that's all the means that are defined by the Milan
Gotcha.
specifications, that you use the same PTP profile, that you have the formats, the timestamps are actually embedded into the audio streams, and there is a dedicated stream format for clocking information, and that information is then used for the clock recovery.
All right, thank you.
Behind you is another question.
Yeah. So it means that basically you're not doing a asynchronous sample rate conversion, right?
No, not at all. We do not.
You
any,
avoid it and just synchronize all the devices using the control loop. Each
Right.
one with the control loop, so you have a synchronized.
Right. We're not doing any compression, and we're not doing any sample rate conversion. It can be done. There's use cases where it might be helpful to do a synchronous sample rate conversion from 48 kilohertz to 96 kilohertz, for instance. Or
but for the small corrections, the standard is to use a synthesizer, a PLL.
Yeah.
Otherwise, asynchronous sample rate conversion could be working anyway, right?
Yeah, that's fairly easy to do. Yes. The other cases where the most issues arise actually is when you have like a AES3 input, for instance, and then you want to get on the network and you have multiple AES3 sources. So what most people do at the moment is you have a AES3 receiver, including sample rate conversion, and you do it already like, here it's called codec, but it could also be a AES3 receiver. Then you do the sample rate conversion there. And on the side, on the XMOS side, on the network side, everything is synchronized.
Synchronized, yeah.
Across the whole network, and then you do not really have to deal with it in software.
Okay, thank you.
But it would also be possible to do it on the XMOS microcontroller, for instance, to run the sample rate conversion there.
Yeah, thank you.
If you have a programmable clock generator where you could change the frequency and the offset, could you do the clock recovery completely in software so that you
won't get that? So what this does actually is also damping the jitter a lot.
Okay.
So what we would get here, so the clock we can generate here would have this accuracy of plus minus 40 nanoseconds, which is still a lot of jitter in terms of audio quality, right? So what this also does is cleaning that jitter. Good, then let's go ahead. I think this is really an important one, and we will also share that. I think we have Richie also following the Discord channel. So we have this in the folder and can drop it there, so you can also use this as a template for your design. I see it's a bit hard to read on the beamer here, sorry for that. But it's good enough to explain the idea. So basically what you see here is a list of all the pins. So this column lists all the pin names on the device. And you have an overview here whether this pin supports a 1-bit port, a 4-bit port, 8, 16, 32. So typically we look at the 1-bit ports and the 4-bit ports. So here we want to choose, like for this PLL sync signal, that's the signal we're sending to the PLL with our clock reference. We typically want to use a 1-bit port. And that's something you can easily assign to any other 1-bit port. So that's really a configuration you make like in the top of your main XC file. You can say, okay, I want to assign it to another port because maybe that's more suitable for your hardware layout. Then you can do that. And that's exactly the point where the electronics engineer needs to talk with the software engineer, because this is something that you as a software engineer configure in the code, but it also has an implication on the hardware. That's why I'm highlighting this so much. You can just do a quick run through the signals here. So we have the PLL sync signal, which is going to the PLL. We have a quad SPI interface here, interfacing with a flash component, so we can persist data. Then we have a couple of serial data lines which can be used for I2S or TDM. So again, typically 1-bit ports. The master clock. And yeah, you can choose if you want to have some level meter LEDs. This can be a 4-bit port, and you pick a 1-bit port for things like this. I think I forgot to mention the I2C interface, which is also being used to configure the PLL. And we have this X-Link system is also used for debugging, so you get a fairly high throughput through the debugging interface there. That's the overview of one of the tiles, and the second tile is mostly doing the RGMII interface. So you have all these Ethernet TX clocks, RX clocks, 4 data lines for each direction, and a serial management interface to configure the Ethernet PHY, or if you use a switch, that would also be configured through that. Is there questions related to that? Then we go directly into the schematic. And yeah, please feel free to drop questions here. In the last webinar, we just did a quick overview over that. So feel free to highlight those questions where you think it's more interesting. First page shows the XMOS microcontroller with all the signals that we have also in the spreadsheet. So this is mostly still something where it makes sense that a software developer and an electronics engineer sit together to define how you want to have this layout. Some electronic engineers prefer to do schematic first, and then they hand over to another PCB layout engineer, which then I experience often ends up in layouts that are more complicated than they need to be. So what I really prefer is to do this step together where I can already look at the layout, because you can optimize a lot. So if you see that signals are crossing and you have the flexibility to assign a 1-bit port to the other side of the microcontroller, then do that. The only thing that is important to consider is that the functionality stays within one tile. So if you, for the clock recovery, have a thread sitting on tile 1, and that is driving a 1-bit port on tile 1, then you cannot move the clock recovery thread to tile 0. You need to have GPIOs and the related software functionality on one tile. That's, I think, the most important part to consider here. But besides that, you can then freely assign ports and swap them. And that's quite efficient to do if you can already look at the layout, get an understanding where signals are crossing, and then optimize. So often you can do this on a 4-layer board and don't need to get much more complicated. Typically maximum a 6-layer board to do a design like this. In terms of power supplies, what we need for the XMOS is a 1-volt power supply and a 3.3. The 3.3 is quite common and needed everywhere anyway. And then also, depending on what Ethernet PHY you use and how you want to use it, most of them have the flexibility to use a 2.5-volt supply, but some can also generate that internally. So really depends. So it's 2 to 3 power supplies that you need. And what we also have here is a bit of logic and power good detection, so you can control the boot sequence. So you want to come up with a 3.3 supply first, 1-volt supply, and then you take the XMOS out of reset. So that's sometimes an issue on the initial bring up, that you stumble across that yeah, it's not coming up. You cannot connect with a debugger. First thing to look at is this reset logic. Of course, check the power supplies. That's pretty standard, but I think good to know that there's something going on there. By the way, we will also share this PDF. So Richie, if you're listening, you can also drop that on the Discord channel. And this is the PLL circuit. So actually not that much, but very important. It's like really, it's the heart of the whole system. Without that, no clocking will work, no audio transfer. So what we have here is typically a standard oscillator. A little optimization we can do is to use the same oscillator for the XMOS system clock, but also as a reference for the PLL. So this is the PLL part where we're getting in this sync signal. And as an output, we get the master clock. And here it's just buffered again. And from there, we send it to the codecs and to the XMOS. Questions related to that? Do you want to go a bit more into design aspects of the electronics, or is it sufficient as an overview? All good?
Do you actually sell reference boards that already do all that stuff? Like for
I think I'm not allowed to pitch it in this presentation, but this stuff here is available here.
Okay, so for people who don't want to mess up with the electronic, it is possible to find some hardware which already has.
Absolutely, yeah. What we often see is that people go directly into the design and start without a reference design. What's quite helpful to have is to have something to test again. So if your isn't working, it's good to have something where you know it's already verified and works. And yeah, I think sometimes you might have an electronics engineer who is coming more from the analog world and is not yet that familiar with digital stuff. For them, they often know the I2S TDM things, DSP is maybe already used, but often the clocking thing is a new thing, and this is the Ethernet part, which is the other new thing. It's the whole Ethernet PHY and magnetics and RJ45 all on one sheet, so it's not that much. But overall, so in this case, we have just implemented a 100 Mbit connection. We would have twice the magnetics if it's gigabit, but the rest would pretty much look the same. RJ45, you can also get PoEs getting quite common. So if you get the full schematic, you will also see a PoE module powering the whole thing. And yeah, on that side, we have then the HMI interface where we interface with XMOS. Also quite important to consider is some pin strapping. You see some pull-ups or pull-downs here, which are used to configure as well the XMOS, but also the Ethernet PHY. So these things are also highlighted in the spreadsheet to get that configuration right. And in this case, we also have another internal power supply, which is driven from the Ethernet PHY, generating Ethernet-specific supply voltages down here. Yeah, just a quick note on layout considerations. What you see in this picture quite nice is how the length matching is done. So these traces from the HMI bus, you want to have them length matched. You have the requirements listed here. For 100 Mbits, it's a bit more loose than for gigabit. If you have short traces like here where it's really super close together, you do not care about serial termination. If the distance is a bit more, then take proper care of termination resistors. Length matching, and then on the other side where we go Ethernet, you have diff pairs. So you also want to match those, and you want to control the impedance a bit to be in this 100 ohm range. And one configuration here, which again affects both software and hardware, is HMI defines that the clock delays a half bit time. So you have an offset between the clock for the transfer and the data, which can be done in hardware, but we can also delay it in software. So that's something to look at if it initially doesn't work. Just make sure that you are aligned whether this configuration applies in software or not. yeah, there was the question about the reference design. So this is what we will also use in the demo now. What we have on these boards is a codec with 2 analog AD channels, 2 DA channels. We have the PLL sitting on that board. Yeah, that's what we will focus on. We can do an audio measurement here, just to see that audio is really getting through. We have the BNC connectors with the left-right clock. Well, it's easier to show it here. We have the BNC connectors which have the left-right clock on it, where we can then nicely see if it's getting regulated and how they sync to each other. And yeah, that's the main considerations for today. And then last but not least, of course, you have some software to configure, and that's still common between our solution, but also the original reference design. There is a file called AVB_conf, a header file where we have defines for the number of channels, the number of I2S or TDM inputs, outputs, the number of streams, the sample rate, all these things that get typically reconfigured. And you have a main file where you then list all the threads. So we can also take a closer look at that if you like. But I think it's pretty straightforward. So there you will find an instance starting the PTP thread. You find an instance starting the serial management interface for the file. You have the RGMII. You have the talker, the listener. So it's really just instantiating and assigning the threads to the hardware cores that we explained before. Good. Then, yeah, maybe a quick run through redundant network setups. This is now getting back a bit to protocol theory, not so much a design consideration. There's a protocol called rapid spanning tree, where the basic idea is that you can build a ring topology with your switches, and RSTP would figure out to disable one of the links because Ethernet doesn't allow to build such a ring. That would cause an overload situation across the whole network. So this link would be disabled. But if another link fails, so like let's assume this one is failing, then the other link can be activated. So this takes a bit of time to reconfigure the network, but it is a sort of redundancy that is implemented in AVB switches and part of the standard. But it's not glitchless. So you would get an audio interruption, but then you would come back to a functional state of the network. There is a risk related to that, and that's why some manufacturers recommend not to use it, which is if you have a ring topology, RSTP can make a lot of sense, but then if you have devices, daisy chaining, like you have an endpoint with 2 ports and it's also behaving as a switch, and these guys down here run RSTP, and the link fails here, it can cause an interruption on the ring back there. Also, the issue isn't up there. Yeah? We still have these connections as before. It can result in a reconfiguration up here. And that's what could cause a glitch in another place in the system where you wouldn't expect it because the issue is here. So maybe you would expect that just this endpoint is failing here. But it can have an effect on something that is connected on another leg here. So that's important to keep in mind and maybe to consider when you use other gear or if you make design considerations for your own product, whether you want to have RSTP enabled or not, or if you provide it as an option and that you educate users accordingly. Not relevant for a simple endpoint with a single port, but if you do a more advanced product with daisy chaining, then this is to be taken into account. And this is just AVB, basically. This is something defined for the switches, not really for the endpoint. So it just applies to these bridged endpoints. What is defined for the endpoints is what we call seamless redundancy, or sometimes it's referred to as AB network. So this is what you also know from other network solutions. So the basic idea is if you have an endpoint here, you provide it with 2 ports, not behaving as a bridge, just as 2 independent endpoint ports, and then you build 2 independent network infrastructures. And you have another endpoint. Let's say this is the one sending, this is the one receiving. You have 2 independent paths for your audio signal. So if a connection over here would fail, you would still have the other one active. And this is something that really works seamless without any audio interruption. And this mechanism is defined in the Milan specifications. Practically, in terms of integrating that, the way it would work is that often you see these Marvell parts, which are switches, basically, and that can then be controlled from the XMOS microcontroller. So you would have 2 RJ45s, transformers. You have the Marvell switch behaving as a 3-port switch, basically. Can also be a 4-port switch and interface with some other host CPU. And then doing the XMOS still behaving as an endpoint, but also managing the switch. So a misunderstanding I sometimes faced with engineers is that they think, oh, this is an AVB capable switch, so it's doing all these protocols for stream reservation and so on. No, what it does is basically filtering, forwarding, traffic shaping. But in order to configure that, I need to run those protocols on a microcontroller sitting next to the switch and translating that into the configuration for the switch. So don't fall into that trap to assume just because it's labeled AVB, it does everything. It's just doing what needs to be done in hardware, but there is still this protocol layer that you need to handle somehow. Good, then I would take another short break now, and then we can take a closer look into the setup here. Also feel free to move around and come closer. There was a question about Apple AVB. That's something we can also try out. And yeah, I will just show some measurements and basic troubleshooting techniques.
The XMOS chip, do you know if it's something that for procurement of it, is it long lead times, or is it something that's easy to, like, getting back to the challenges of having hardware on time on shelves? If we design something based on that one, how quick can we procure the XMOS?
Of course, you know, maybe better, but you're also more on the software side. No, I think samples are always available, and of course, depending on your volume, you need to talk to the distributors or XMOS directly. But we have not really experienced issues so far. So even during the supply chain crisis, it was still pretty good. Yeah.
Okay.
But of course, it's always a very individual consideration. So maybe also a general recommendation for the whole design process to consider that early, bring that question up, not at this point in the end, but like when you have done the schematic, do it early when you choose the package, which is part of this consideration. When you work with a spreadsheet, get in touch with the distributors and clarify those questions, and then you usually have enough time during the design process to get the right number of parts. But that's a general advice for anything you do and any component you have in the system.
And maybe another general question about AVB in general. So many of these audio over IP are concerned with focusing extremely on audio. It's about transmitting.
Mm-hmm.
How much does Milan say allow metadata in the streams, or do they care at all about transmitting something that is related to the channels, or is it like you have a channel identifier and then you...
Mm-hmm. So as you see in this very early slide at the beginning, we define it like there's Milan sitting on this application layer, which is currently just in the scope of audio. which does not mean that it's not open to define other things. So if there would be a vendor coming in and say, hey, the concept of Milan is great and we want to do video, why not? It's possible. You would define something for that. Like on the application layer, if you want to say, okay, we want to set a standard for video, and we want to have that interoperable, it would make sense to copy the concept, what we did for audio, for video, and it could be part of the whole Milan specification thing. That's one consideration. The other is on the AVB technology layer, it does not interfere. So if you have another AVB system doing a video stream, that's totally fine. The switch does not really care whether it's a Milan stream or another.
That's not what I had in mind. Like if I wanted to identify a particular stream as being the guitar, another one as being the vocals or something like that, is there any mechanism of identification?
Yeah, of course. Yeah. We will take a look at in the demo. So there's mechanisms to set device names. You can. We can have a look at all these descriptors, which is a nice overview, I think, also to understand a bit better the AVDEC protocol. And there's many possibilities to assign names to channels, assign names to streams, and all those things. Yeah.
We have a question from Mark on Zoom. They're asking, where can we purchase the reference design boards? They see it on the website, but nowhere to buy it.
I told you that I'm not allowed to pitch our solution, but you find our contact information, just reach out and find a solution for that. All right, then let's meet in. Is 5 minutes enough, or was it a bit short? I think it was slightly more. Let's meet 10 to 12. Then I promise this is the last couple of slides, and then it will be more hands-on. So what we basically have here is a network composed of 4 of these reference designs with a Netgear switch and my laptop being connected to it in order to control that. And what we have in terms of controllers is there's currently 3 solutions out there that I would consider as being usable. One is called Hive. It's an open source project based on the AVDEC library from Acoustics. Thanks for providing that. And then one of their developers, I think it is more of a hobby project, but one of the guys who we work with closely in the Plugfest at Avenue Alliance and the standardization developed this as a tool, which I would say is not super user-friendly, but it's a very useful tool for the development process, because you can really go through all the descriptors and everything. So I will also use this in the demo today, because I think it's really the developer tool you should know. And then also very important is the Milan Manager, which was developed in a collaboration from D&B and Acoustics, but it's neutrally branded and considered to be the controller that can be used by any Milan vendor. And another solution which has a bit a different approach, more visual, like you can drag and drop connections, is from Maya Sound called Nibra. Also free to use, so you can download these. Hive was also, or I think all of them were listed in the list of links. So feel free to download that, and also if you want to plug it in here and play around with this network a bit, feel free to come over during this hands-on session now. So just a couple of notes on how to troubleshoot. Of course, everything is built to be plug and play, at least for the users at the end, but as a developer, you might come across some situations. And this is a slide I added very spontaneously this morning, as I got this Netgear switch, and this wasn't part of my test setup before. And there, it's really built for AV protocols, and they have all these profiles that you can load, but this one configuration step you need to take is to enable AVB. So if this is not done, if AVB is not yet enabled on the switch, this is how it will look like in the Hive controller. It's a little bit hard to see, but you have these red dots here. And yes, the legend for that is a bit nerdy. There's many different color codes, but red means there's something wrong. And something you can really look at is going to the overview here, where all the devices on the network were discovered. And there you find a parameter Grandmaster ID. The Grandmaster is the device in the network providing the PTP clock reference. So this is not necessarily an endpoint. This can also be the Grandmaster ID of a switch. But what we see here basically is that the Grandmaster ID refers, it's derived from the MAC address, which means each endpoint has its own Grandmaster. So the device itself is the only Grandmaster. Why? Because this path delay measurement gave the result that it's above the threshold, which basically happens because AVB, GPTP is not enabled in the switch. So that's a picture you will find if a user uses a switch that is not AVB enabled. So pretty easy to spot if you know about this. Just have a look at the Grandmaster IDs, all these red dots. And then after we enabled it, maybe we can also show that if you want to take a closer look, but it's pretty straightforward. There's a configuration software called Engage. You find the switch, you can load the AVB profile, and once that got enabled, we had it solved. The other thing we can look at today is the clock recovery. So just quick recap, we have the circuit with the XMOS generating the sync reference for the PLL. We generate the master clock there, that's fed back to the XMOS, where we then generate the left-right clock. And the boards are prepared to look at this left-right clock, so we can easily access it here on the BNC connector. And this is what we have connected to the oscilloscope from 2 boards. So in our whole setup, this is how it looks like. We have the network connections through the switch, and we can pick 2 boards to connect to the oscilloscope to verify that the media clocks are synchronizing. I'm just going through that now to give you a quick overview what we will do, and then we will be hands-on. Then I don't have to switch back and forth, but we will take more time with these cases. When it comes to protocol troubleshooting, there is something that you can do fairly easily, but it has its limitations. You can use Wireshark on the laptop where you're running the controller, but it's important to note what you will see there is just what's going on the laptop, basically. So everything related to the control protocol, to ATDEC, basically, is what you can troubleshoot here. So if anything is going wrong in the controller. What you cannot see there is what's going on in terms of PTP between the switch and the endpoint, or you cannot see what's going on in terms of stream reservation protocol between these devices. There's a question.
Is there any specific requirement to the network adapter used on a control device to configure an AVB network, or can we just use a normal network USB dongle? Because I know there are some Apple dongles specifically specified for AVB, but I guess this is not about configuration, but about actual audio streaming. Right. Am I correct there?
Very good question. So what I'm using in the setup here today is this D-Log 5 adapter, nothing special. But I only use it for this control aspect. There's not going any AVB streams through that connection. And it does not have to act as a AVB endpoint. It does not have to do PTP. It's really just control stuff. So that goes through any network interface. Where we need these AVB capabilities is on the endpoint and on the switch, but not on the remote control. If you, and we also have this case here, we have someone with a MacBook, and there is a special adapter from Sonnet. So this can be used to get this AVB capabilities on a Mac, and then you can also have the Mac as a AVB endpoint and get audio through. But then you have these requirements on the Ethernet dongle to do the timestamping and these things.
I'm not sure if it's the Ethernet dongle per se, or if it's that they do the Thunderbolt thing. If it was any Thunderbolt adapter, that would work.
I would guess that the timestamping is really done on the Ethernet 5, which is probably in the dongle. But I do not know exactly. But
I've seen someone using the
so.
Ethernet port at the back of their screen, which is connected by Thunderbolt to the Mac, on one of the YouTube demos.
Unfortunately, I cannot look into their code, so I'm not really in the details. But yeah, what you want to do to be precise in the timestamping is you want to do the timestamping in hardware, like no buffer in between. So that's what gives you the accuracy.
And it's not the Mac doing it; it's actually the dongle.
The Ethernet Mac in the dongle, not the Apple Mac. Yeah.
So I have a question about capturing for Wireshark. If the switch supports port mirroring, will that allow us to see the PTP negotiation?
Also a very good question. It's a technique I have used back then a lot, but I stopped doing it completely. So let's say you want to debug PTP on this connection here, and you mirror the traffic from this port over to this one. Yes, then you would see what's going on here, but the switch might still try to do PTP on this port to do the path delay measurement. So you see path delay measurements from here and here, which is super confusing when you're debugging it. Of course, you could filter for the port ID and things like that, but I found it too cumbersome. So I really stopped doing it. And it can really be confusing, and it can also lead to unexpected behavior, which makes, again, the debugging even more complicated. So what we typically try to do, as all these things going on here are real time, we try to not influence that. We might want to probe something here, which I will show on the next slide, but we try to have the least impact on all these real time aspects.
So is there another way to visualize that or debug?
Yes, I have prepared that. So what you can do is use a Ethernet tab, which is basically Ethernet in out. So you can rip up that connection basically and put it in between. There is this company called ProfiTab, or the ProfiShark is a tool used a lot, which is a good investment because you also need it for the certification setup if you want to own and run your own. There also these devices are used. Comes with a nice software suite also to run on Windows. So today I will also use that in the demo. That's quite easy to use and to set up. You can capture the files, analyze it, pretty straightforward. And it has the capability to do very precise timestamping as well. However, there's another solution I would like to mention. The same functionality at the first glance. It's called the Ethernet debugger from a German company called Intona, which is a bit more affordable and allows much more, has a nice suite of tools that allow scripting when you are in a Linux environment especially. So we use this stuff a lot in all our test setups. Has some nice features, PoE through, stuff like that. So also a nice handy tool. But the basic idea is the same. Get a probe in between this connection. What's important to consider there is what it changes is it adds delay to the path delay measurement. So if you have already a 100-meter connection here and you have this, you would get into the range of a path delay of 400 nanoseconds. And let's assume it's a 100 Mbit connection. then you get into a range where you are beyond the P-delay threshold, which is set at 800 nanoseconds. So for 100 Mbit, this is really becoming an issue. So now you can compensate for that if you tweak the endpoint and you tweak the P-delay measurement to compensate for that delay. You would still get a valid PTP connection here. It's less of an issue if you're a gigabit. So these devices are fast enough. They still add a bit of delay, but it's still below this threshold. So of course, it adds some delay, but it does not really change the behavior of the network. But this is really something to consider because the switch would figure out based on the path delay measurement whether this connection is, we often call it AS capable. AS is 802.1 AS, and then we say AS capable. Means it does proper PTP, and we take that usually as an indication that it's AVB compliant and we can do streaming and everything here. So that's a criteria that the switch would use to enable AVB on that port. And for debugging, we still want to have it enabled, of course. So another problem when you're on gigabit and if the cable is not too long, if it's 100 Mbit, then we typically tweak it in the PTP implementation to adjust the P delay. Good. Yeah, that's it in terms of theoretical setup description. I will now switch to Hive first to show you how this looks like. There's basically two modes. So when you start Hive for the first time, you can choose whether you are in the user-oriented mode, where it's just about making connections, so you end up in a view like this. Or I typically call it the nerd view. There is a list of discovered entities, and then you can also enable the entity model inspector. And I think this is maybe interesting to take a bit time for in this case, because this gives you a lot of capabilities actually to also design your workflows or your own user interface, because there's really a lot of information available in this entity model. So the structure of that is that you basically have an entity model descriptor, which contains this information like entity names. You can set up group name. So I can just click there, set it, and change it to something. Let's say it's the ADC 24 group, and then it's getting set there. And you could use that for filtering later when you do connection management in a more complicated setup or something like that. You have an entity model ID. You have a lot of flags and details, serial numbers, MAC addresses. That's often information that's useful to have. And the entity model descriptor also contains basic information like how many configurations are there. Typically, we have then one step further down the entity tree. We have typically one configuration, but could also be many configurations. And a configuration then contains these descriptors for things like the audio unit, which is an abstraction of the things like the sample rate. There is the stream ports that contains the audio mappings, things like that. Audio mapping is basically the routing from a stream to the I2S channel. So yeah, we can take a look at that. And when we have a stream input, you really see you see a lot of plain data here, but then there's also things where you can click the edit button here, and then there's a more visual approach. So like I told you, you have, as a listener, you have to support this 8-channel stream format, but maybe you have just, as a loudspeaker, just a single channel, or in our example, we have just 2 analog channels out there. So you need a mechanism to pick the channel from the stream. So there might be channel 8 that I want to play out on that loudspeaker over there, but channel 1 on the other loudspeaker over there. So then you can drag and drop a connection here and do that. And that's a must-have feature for every Milan device. There's questions over there?
Is there any particular protocol it uses for discovery?
Yes, the whole set of protocols is called ATDEC, defined in IEEE standard 1722.1. And actually, ATDEC is a set of multiple sub-protocols. So there's something called ACMP for the connection management protocol. There is the enumeration, discovery, enumeration to get all this. All this information actually comes from the entity. So this is stored in the entity and is dynamically transferred to the controller. So the controller doesn't have any knowledge about the model it's connecting to here. Yeah, then for the connection management, there's also a sequence going on where the controller informs the listener what talker to connect to, but then the communication continues between the listener and the talker. So this information can also get persisted on the device. So without the involvement of this software, the network can come up after a power failure and re-establish this connection, for instance. So that's a set of various protocols, actually. Yeah, then going further here, we see we have a stream input descriptor for CRF. CRF is the clock reference format, so that's a stream format that doesn't contain any audio data. It's just clock information, just the plain timestamp. And then here on the second stream, we have an input stream where we can now also see the stream format. So it's AAF encoding, 48 kilohertz. What is this saying? PCM encoding 32-bit 8 channels. And you also see here that on the receiving side, I have to be Milan compliant. I have 1, 2, 4, 6, 8 channels are supported here. On the sending side then, if you look at stream output 1, we have just one format. The talker is allowed to choose just one format, and here we have 2 analog input channels. So the format we choose as a vendor of this device is just a 2-channel format. What you can also see in these descriptors is a lot of information related to the stream reservation. So you see stuff like the stream ID, some flags that give you an indication if the stream reservation was successful or if it failed. And what's also quite useful to provide status information to users is these counters. So you can see here how often was the stream started, how often was it stopped, was there an interruption on the media clock. Let's say something is changing on the network because you connect other switches, the GPTP grandmaster may change. Then you would also get a flag here that the timestamp is uncertain, and you just have a counter that shows you how many frames got sent. And of course, you have the same thing on the receiving side. There it's even a bit more. So here we can see if the media was locked, if the media is unlocked, if we had timestamps that were too far in the future, or if the packet arrived too late, which might be a case if you have like 30 hops, it might not work. So then you would see it in a late timestamp here, how many frames were received. So also, used almost on a daily basis to see, okay, I made a connection, but it's not coming, so something is broken in my implementation. And then to finalize the overview of the descriptors, there's a descriptor for the interface itself. So there we are counting the total numbers of packets sent. No, not in this case, sorry. But what we still see is we have a link up-down counter. We have grandmaster changes are detected here. So if I plug it in and out again, this would increase, or if another switch with a higher priority comes into the network, the grandmaster might get re-elected. Then we would also indicate this. Where this is helpful is if customer comes to you and says, I had an audio dropout, something is wrong with the audio. Maybe it's not the audio, maybe it is just someone who plugged in another switch. So you want then to look at these data, say, okay, yeah, your grandmaster changed, so the consequence was that your clocking was interrupted, therefore you had the audio dropout. It's not really an audio issue, it's maybe more a setup issue. And last but not least, well, there's a bit more. This is an optional thing, not standard for Milan, but also defined in the ATTech standard for firmware upgrades. So this is something we have implemented here, so we can upload the firmware. You can implement locals, but not mandatory. And when we have a setup like this, where all devices have the default names, so it always says joint AVB on Panda-Board, so I cannot really identify what device is what. So what I can do there is I can click on the device and enable this identify control descriptor. And then I have a LED blinking here, only on that device. So I know this is the one that is, let's call it, I don't know, it's the black board. And I can go through my list, do that step by step for each of them. Again, identify, so this is the other one back there, so I call it black back. And let's see who this is. That's the green one here in the front, which is also connected to the oscilloscope. I think I edited the wrong one. This is the green one. Back. And I really need that in order not to confuse it in the further demo. Good. And then the clock domain descriptor, this holds one important control, which is the current clock source. So there's always the scheme that you can run on an internal oscillator. Theoretically, you could also implement an external clock source, like a word clock input on a BNC, then it would be selectable there. And of course, if we want to sync to another endpoint, then we need to have the capability to sync to a clock stream or to an incoming audio stream. Both contain always the timestamp information. So both is possible. It's quite common to use the clock reference stream. And there's also a new feature which makes the setup even a bit easier. So you don't have, if this is set as a default, then you don't have to deal that much with clocking. To have a PTP-derived media clock, that's the option 0 up here, which is a new feature in Milan, but also standardized across everyone who's supporting it, which basically is a mode quite similar to what AES67 is doing. In AES67, you take the media clock is always directly related to PTP. As we clarified before, we are having a common PTP time, and then we reference just the media clock to that time, and we regenerate the media clock, but it's two independent things. With this, we can choose this other mode where we just generate the media clock based on the PTP time, which is also quite handy. And if this is set on all devices, then I don't need to deal with this other clock source settings. So actually, we should make this maybe a default again. Currently, I see it's not. Currently, the internal clock is the default. So I'm setting all to PTP now. And if you look at the oscilloscope now, it should sync. Is it? It's taking a bit time, but I think we're getting there. And of course, as this is still a early implementation, it's not perfect, it's not in phase, but it's synchronized. So still room for improvement there, obviously. Going back to the other mode, maybe so we can, let's say we choose the green. Let's maybe make it easier by disconnecting this one as we're not using it at the moment. So we have just two devices here. You now see it's turning red for a moment. There's something going on. Master change. Reloading it, everything is cleaner. I've just reloaded it because it's going a bit faster than waiting for the update. Now we can say, let's say we take the green one, we set it to internal, so we're taking the media clock from there, and we're making a clock stream connection over to the black board. And on the black one, we choose the clock source CRF. And it should synchronize again. If we switch to the camera here, you can see it. And now we see it's really precisely synced on the edges. This is how it should also be for PTP. If we zoom in a bit here, not familiar with this OSCE, but position set to 0. Where can I see the time? Yeah, so this is a 21 box. The lighting is really bad, right? Can we get it better? Can you stand there, please? Yeah, that's good. Perfect. So one division here is 25 nanoseconds. So we see it's wandering a bit within this range of, now it got a bit further, 50 nanoseconds, but it stays in sync typically in this range of plus minus. I would expect something like plus minus 40 nanoseconds because that's the resolution we can really measure. But slowly drifting, not really chittering. So we have a very precise synchronization here. Questions related to that? And that's actually a test I recommend to have, like when you're currently developing, doing audio measurements with their setup, even if it's not directly related to the AVB implementation itself, but especially when you are working on these things. So this is a measurement I have like on my desk every day. It's the most tricky part. It's the most important part to get right, to get good audio quality through. And it's an indication for so many things, like if I would have an issue on the switch and the grandmaster is changing, if PTP is behaving badly, this cannot work. If the clock recovery, this whole PID control loop is not working, it would end up here. If the stream sending is not working, I would see it here. If the receiving is not working here. So this is like one of the, let's say, silent tests that you can have running all the time. Of course, the other test is just get audio through, and then you would also hear it. But even there, you would see a sync issue probably before you hear it, because the clocks would start drifting, and then it can still take minutes until you hear a click, because you really get an over or underflow on the audio buffer. So highly recommended to have this test running, and also when you're more on the analog side and looking at the audio signal, of course, you would also see distortions there, but the root cause might be something in the clocking. So therefore, quite valuable to run that. I think in terms of time, we have to come to an end, right? Room, I want to thank you for your interest and the attention, and happy to stay in touch. And feel free to join the setup for the remaining session. Thank you.